Stuck on CNA labs? Tired of scattered tutorials? This full course covers every exam topic with real lab configs. Grab your free lab in the description. Ready to pass CNA and boost your career? Start now!
Hello, friend. In this lesson, we'll learn about the ARP protocol. ARP is also called the Address Resolution Protocol. After completing this chapter, you should understand the basic workings of ARP and understand our ARP cache table, its function. First, let's look at why we need a protocol like ARP and what its role is. When one of our hosts needs to communicate with another host, at this point, for example, our host 10.1.1 here needs to communicate with host 10.1.2 in the network layer encapsulation packet. Its source IP address and destination IP address are already determined. Right. When these packets are handed to our data link layer for framing, a frame header is needed here. In the frame header, there will be a source MAC and destination MAC address. These two items are present. The source MAC address is simply the MAC address of its own network card. This is known. Nope, but what about my target host, 10.1.2? This host. What is the MAC address of its network card? I don't know it right now. Right, so, to encapsulate this packet, I need to obtain the peer's information. The target host I need to communicate with. Its destination MAC address. I need to get its MAC address. So, how do we get it? This is where ARP comes into play. By sending an ARP packet to request the other party's MAC address, to obtain the other party's. What is this comparable to? It's comparable to you being on the street and running into a at this point, you see she's quite pretty. Then you ask her for something. For her contact info. Right? So this is like sending a request. Then the other party tells you her contact info. Take this MAC address. This is the basic working principle of ARP. So at this point, host A, right? It will send out an ARP packet to request the target host I want to access, right? What is its MAC address? Note that this packet is sent out as a broadcast. It is sent out as a broadcast. So what is the characteristic of this character? We covered this before, right? All hosts in that broadcast domain will receive it. They will all receive this request process. Inside this ARP packet, it will mark the host I need to request. What is its IP address? Right? For example, this host right now. I send out a request. I'm requesting, what is the MAC address of 10.0.0.3? At this point, after host B receives this request packet, it discards it. Does not process it, then after C receives it. It sees the request is asking for its MAC address, right? So at this, it will reply. It will reply. And then, after receiving this reply, host A will take this corresponding address information and store it in its own cache table. Our host has its own ARP cache table. It records in there, for a certain IP address, what its MAC address is. Yeah, it will record it in this table. Every computer has such a cache table. Any host you've communicated with will have a corresponding ARP record here. Of course, this record also has an aging time. It has a storage duration, right? It cannot stay here forever. Generally speaking, the default is 30 minutes. 30 minutes is a typical storage duration. Of course, some systems store it for 5 minutes. After recording it, it is stored for 5. If, within 5 minutes, no data communication occurs, then this ARP record will be deleted. The next time you need to communicate with that host, well, it will send out an ARP request again. Then the other side will respond. The ARP process will be executed once more. The purpose of this cache table is that once you already have this information, it is placed in the cache. If subsequent packets need to communicate with this host C, you no longer need to frequently send ARP pack. You can directly use the record from the cache table. Right? Fill it in the destination MAC address field, and the packet can be sent out directly. This improves communication efficiency. Otherwise, Well, sending an ARP for every single packet. That is just not very suitable. Okay. The ARP request process works like this. Our host A sends it out as a broadcast. When broadcasting, the destination MAC address is all FS. All FS. Then, the source MAC is its own MAC address. Right? Then in the ARP content, it will ask for the target host I am requesting, right? And who I am. I'm 10.0.1. Now I want to request the MAC address of 10.0.0.3. Then the source MAC is my own MAC address, right? So what about the destination MAC? It is empty, because right now I don't know this host's MAC address, right? And the operation type is request. That means a request. So after the other party receives this packet, it will respond, right? When responding, then it will tell our host. Tell our host what the corresponding MAC address is. Meanwhile, in C's ARP table, because we just received the ARP request packet from A. In this request packet, it clearly marks what MAC address 10.0.0.1 corresponds to. So C will record it. Will record, and the method is dynamic recording. That is, this MAC address was learned dynamically. Some binding relationships between MAC addresses and IP addresses. The relationship between IP and MAC. We call this an ARP entry, right? Some of these entries are statically bound. Some are statically bound. And some are fixed. For example, its own MAC address. Its own IP and MAC address. So it will also have this. This one is permanent. As long as these interfaces on your device, it will exist, and some are manually configured by us. Configured on this host via the command line. Like in Windows, right? You can use commands to take a specific IP address and its MAC address and bind them directly. Sometimes, for example, when under some kind of attack, like an ARP spoofing, we can use static binding to permanently bind the gateway's IP and MAC address. Right, this prevents attacks like ARP spoofing. So this is about the type. There are several ways. So if it is learned through ARP, it is generally this dynamic type. Which means dynamic. And then, C also needs to reply to RA. This request, it needs to reply. Send a response back to it. Send a response inside the reply packet. It will include itself, right? Who it is, and who it is replying to. Right, who it is, and pay attention to this reply packet. The reply packet responding to the ARP request. This packet. It is sent back as a unicast. And no longer as a broadcast. Because it is very clear what the destination IP address is, right? And the MAC address is also available. So it just needs to be sent as a unicast. The request must be sent as a broadcast. Because we simply don't know, right? Where this host is located. And who is this? This 10.0.3, right? So at this point, it's a broadcast. It's basically calling out for someone, right? So at this point, it's a broadcast. It's basically right? You don't know where this, looking for someone, so broadcast it. As for the reply, it's sent as a unicast. And it will mark its own MAC address here. Once this MAC address, the other party, after host A receives it, it stores it in A's ARP cache table. Right? Which IP maps to which MAC, and what was the learning method? Right? Everything is recorded. In this way, both A and C have an ARP cache table. For subsequent when sending packets, it directly calls the MAC address recorded in this cache table. Then just sends it as unicast. That's it. What we just discussed is the basic working principle of ARP. However, sometimes, the host we are communicating with is not in our broadcast domain. Right? Because our basic ARP query, the ARP request and reply, etc. Since it requests in broadcast form, within a single broadcast domain, this is not a problem, but in a situation, our two hosts are not in the same broadcast domain. They are in two broadcast domains, right? This side is one broadcast domain. This side is another. Okay, so at this point, if A wants to communicate with the other party, I need to get the other party's MAC address, right? So at this point, it sends an ARP request. An ARP request. Right? Sent out as a broadcast. But it stops right here. Right? The ARP request cannot be forwarded from here. Right, it can't. So, there's a very important feature for this. Called proxy ARP. Called proxy ARP. What does proxy ARP mean? Well, it's when this feature is generally configured on the gateway. Generally configured on the gateway. Yes. Its purpose is, when someone sends an ARP request, if it discovers the requested IP address and the corresponding host's IP address are not on the same network segment, not on its own local network segment. Right? Your site is on 10.1. But you're requesting an address in the 10.2 range. Right, it finds they are not on the same network segment. At this moment, the ARP gateway, this gateway interface, will respond to the ARP request on behalf of the target host. It performs the ARP, that is, the gateway interface stands in for your target host to issue the ARP reply. The request reply. Right? The MAC address contained inside is our interface's address. The MAC address of this G0/0 interface. Then, when host A communicates with B, the source IP and the destination IP remain as 10.2.0.1. The IP layer remains unchanged. However, at the MAC address level, right at that layer, the source MAC is still A's MAC address. But who is the destination MAC? The destination MAC is the G0/0 interface's MAC address. It is this MAC address, right? Because our gateway interface generated the ARP reply. In that case, the packet can be encapsulated normally, right? All conditions are met now. Then it can be sent out. After it is sent, does this packet arrive at our gateway? So, when the gateway receives this packet, based on the original destination IP address, it performs route selection. This enables right? It finds that the destination is in this network segment and needs to send the packet out from this interface. At this point, our gateway. Right. Well, it's the same. The original source and destination IPs, right? Now, what about this? Well, this is its own interface. Right? Then, what about the at this time, it will send an ARP request. It sends an ARP, and then host B will give a normal reply. Now the destination MAC is also available. Right? Then the packet can be sent back. If there are other routers in between, it's the same process. Once the router's interface discovers that the MAC address you requested, right, the destination IP in your ARP packet, and the IP address of the interface you're requesting, are not in the same network segment, at that moment, it will send an ARP reply, which is the process of proxy ARP. It replies on behalf of the target host you requested. And then you encapsulate the packet, right? So the packet can be transmitted normally here. Therefore, within each network segment, within every network segment, once your packet needs cross-network transmission, you will find that the original source and destination IPs remain unchanged. They remain unchanged, whether it's from A to B, or across many routers in between. Right? No matter how many, the original source and destination IPs here stay the same. But the original source and destination MAC addresses do not stay the same. It changes. We mentioned before. In the OSI 7-layer network model, the role of the data link layer is to transmit frames from one node to another. When you cross network segments, within this link, it's this node-to-node transmission. Right? Transmission from this node to this node. So here, the source and destination are replaced by the MAC addresses of this interface and the peer interface. For every layer 3 link, every network or every broadcast domain, when you need to cross it, its source and destination MAC addresses will change. But the source and destination IP addresses remain unchanged throughout the entire transmission, because it provides network reachability. This provides node-to-node transmission. Right? This was covered in the OSI model earlier. When discussing ARP, let's give you a feel for it. Okay. Besides proxy ARP, there is another ARP called gratuitous ARP. This gratuitous ARP is actually used to detect IP address conflicts. Sometimes, for example, you're plugged into the company network. Sometimes a pop-up window will appear saying IP, right? How does that happen? It is detected through gratuitous ARP. When our host accesses the network, it sends a DHCP request to our server to obtain an IP address. Right? After obtaining an IP address, It will send out a gratuitous ARP. It will send out a gratuitous ARP. In gratuitous ARP, note that it is also sent as a broadcast. Also sent as a broadcast. Then both the original destination IP and source IP are itself. But this packet is sent as a broadcast. That means this packet will flood the entire broadcast domain. All hosts in the broadcast domain will receive it. Right? So, if there is a host below us, whose IP address is also 10.0.0.1, right? Then it will discover that this MAC address does not match its own MAC address. Right? Then it knows there is a host with a conflicting IP address in this environment. It can be detected what its current IP address is. Once it connects to, it will send out a gratuitous ARP. Right? It's like you transfer to a new school, right? You enter a new class. And the first thing you need to do, the teacher will ask you to introduce yourself. You have to say who you are. So if in your class, right? If there happens to be someone in the new class whose name is exactly the same, right? It must be resolved on the spot. Right? How should both of you be, right? Okay. Of course, this rarely happens most of the time. Because our IP addresses, the host IP addresses, are assigned one by one. Right? It doesn't happen the concern is some hosts, right? Where someone sets a static IP address on their NIC manually. Then when connecting, an IP address conflict might occur. That's detected using gratuitous ARP. Once detected, the system will alert you. It will pop up right? It tells you our IP addresses have conflicted. Then you need to contact the administrator. Right? These solutions. Okay. So, in this lesson, we discussed the basic working principle of ARP. We also discussed the role of the ARP cache table. Of course, there is actually a deeper knowledge point here. At our CCNA level, we won't go into an in-depth explanation. But you should have an impression in your mind. That is proxy ARP. Proxy ARP. We said that when a host sends a request, once our gateway interface discovers that the requesting host and your host are not on the same IP subnet, it will act on behalf of your target host and make an ARP reply. Right? It makes the ARP reply on behalf of the target host. Then we can normally encapsulate the MAC address. Right? The packet can be sent. That's fine. But if we disable the proxy ARP function on the gateway interface, disable it, then when a request comes in this time, it will no longer reply on behalf of the target host, correct? At this point, can our hostess still get the MAC address of target host B? It cannot get it at this time, right? So it will fail to communicate. It will fail. In fact, for this gateway interface, this router interface, the proxy ARP function is enabled by default. Just don't manually disable it. Right? This is a knowledge point. When you request the MAC address of a remote target host, if the interface on the opposite end does not have proxy ARP enabled, it might cause a communication failure. It might cause a failure. This is an implicit knowledge point about proxy ARP. Of course, there are other knowledge points as well. A deeper supporting point. For example, we'll learn about static routing later. We'll learn about when studying static routing. I suggest configuring the next hop first, rather than the outgoing. The main reason for this is largely because of ARP. We won't go into details here. If you're interested, you can learn about it in the CCNA course later, where you'll get to study. For this lesson, that covers the main content. We discussed how and the role of the cache table.